स्टूडेंट्स एंड वेलकम टू टुडेज सेशन। आज हम डिस्कस करने वाले हैं अबाउट चैप्टर 4 स्ट्रक्चर ऑफ एन एटम। We have already gone through the details about what an atom is in the previous chapter. एक rough idea हमें मिल गया है. In this chapter, in this session, we are going to go into the details about the structure of an atom, right? So we know that structure is एक एटम के अगर हम स्ट्रक्चर की बात करें तो सबसे पहले एटम जो हम अपने आसपास देखते हैं, एवरीथिंग अराउंड अस इज मेड अप ऑफ एटम्स. All matter around us is made up of atoms. And atom जो है वो further divisible नहीं है, but उनके कुछ सब atomic particles के बारे में हम बात करने वाले हैं. It contains subatomic particles that are present inside an atom. And 1900 में जे थॉमसन ने ये सब एटॉमिक पार्टिकल, जिसको हम इलेक्ट्रॉन कहते हैं, नेगेटिवली चार्ज होता है, ये आइडेंटिफाई किया था. बट बिफोर 1900 एज वेल, इन 1886 ई गोल्डस्टीन he discovered the presence of certain radiations in a gas discharge that were called as canal rays. And these rays, they were positively charged radiations, जिनकी वजह से हमने एक और सब एटॉमिक पार्टिकल की डिस्कवरी देखी, which is प्रोटॉन. तो दो सब एटॉमिक पार्टिकल्स हमें पता है एटम के अंदर प्रेजेंट है, इलेक्ट्रॉन्स एंड प्रोटॉन्स, राइट? इलेक्ट्रॉन्स आर नेगेटिवली चार्ज्ड whereas protons are opposite in charge, मतलब they are positively charged. So they are equal in magnitude but opposite in charge. So the subatomic particles हैं, they have a charge, they are equal in magnitude but they are opposite in charges. अगर हम बात करें प्रोटॉन के मास की, तो प्रोटॉन का मास is almost 2000 times as compared to that of electrons. Electrons का मास negligible है, ना के बराबर है, almost, right? Protons का mass is much more than the mass of electrons. Denote करने के लिए we denote electron as E minus and proton as P positive based on the charges that they carry. And the charge of or a mass of a proton is taken as 1 unit and its charge is taken as +1, whereas mass of electron is considered to be as negligible and its charge is taken up as or denoted as -1, right? So the protons and electrons, they balance their charges. Their charges must be balanced. That is why we say that, you know, an atom is stable in nature. And it was also observed that protons को easily extract नहीं किया जा सकता है एक atom से, whereas electrons were relatively easier to remove. So इससे हमें ये पता चला कि protons somewhere they lie inside in the interior of an atom. That is why they are much harder to remove as compared to electrons. So बहुत से साइंटिस्ट ने कुछ थ्योरीज, कुछ मॉडल बताए, रेकमेंड करे कि कैसा एक एटम का स्ट्रक्चर हो सकता है. सो वन ऑफ द फर्स्ट साइंटिस्ट टू डू सो वाज थॉमसन. थॉमसन ने ये सजेस्ट किया दैट द एटम इज सिमिलर टू अ क्रिसमस पुडिंग, जिसमें द इलेक्ट्रॉन्स, दे आर लाइक द ड्राई फ्रूट्स दैट आर प्रेजेंट इन द स्फीयर ऑफ द पुडिंग. तो स्फीयर को उन्होंने एज पॉजिटिवली चार्ज्ड आइडेंटिफाई किया एंड उस पॉजिटिवली चार्ज स्फीयर के ऊपर द इलेक्ट्रॉन्स आर प्रेजेंट in the form of dry fruits. This model can also be compared to the model of a watermelon, in which the red part represents the positively charged particles and the negatively charged particles, that are electrons, are present on this sphere or on this red part in the form of the seeds of the watermelon. तो उन्होंने ये सजेस्ट किया कि एक पॉजिटिवली चार्ज स्फीयर है, एक पॉजिटिवली चार्ज एरिया है, रीजन है, जिसके ऊपर जो नेगेटिव चार्जेस हैं ये प्रेजेंट है, ये एम्बेडेड है या स्कैटर्ड है. तो इनका जो मॉडल है, it proposed that atom consists of a positively charged sphere in which the electrons are embedded, and he also suggested that this positive and negative charges, they are equal in magnitude, jiski wajah se we say that atom it is electrically neutral. Atom as a whole is electrically neutral. इस चीज से, इस थ्योरी से, इस मॉडल से हमें ये तो समझ आ गया दैट यस, एटम्स आर इलेक्ट्रिकली न्यूट्रल, बट जो आगे कुछ साइंटिस्ट ने एक्सपेरिमेंट्स कंडक्ट किए, वो हम उनका जो रिजल्ट्स था, उनका जो कंक्लूजन था, इस मॉडल के बेसिस पे उसको जस्टिफाई नहीं कर पाए, राइट? सो दिस वाज नॉट द करेक्ट मॉडल ऑफ एन एटम. नेक्स्ट जो एक्सपेरिमेंट आया, दैट वाज रदरफोर्ड्स मॉडल ऑफ एन एटम. He designed an experiment which used very fast moving alpha particles, and these fast moving alpha particles, they were made to fall on a thin gold foil. Now the reason he selected a gold foil was because he wanted a very very thin layer, as thin a layer as possible, and the thickness of these gold foil that he used, it was only about 1000 atoms, so it was a very thin layer. And what he did was he allowed alpha particles to move or to fall on this very thin gold foil. Now alpha particles, they are doubly charged helium ions, and they have a mass of 4 units, and they are considered to have a very high, considerable amount of energy. Now it was expected, the result that was expected was that these alpha particles, because there are subatomic particles present inside an atom, तो ये एक्सपेक्ट किया था कि उस सब एटॉमिक पार्टिकल से डिफ्लेक्ट होके ये अल्फा पार्टिकल्स जो है वो डिफ्लेक्शन शो करेंगे, राइट? बट सिंस अल्फा पार्टिकल्स आर मच हेवियर than the protons, he did not expect to see major deflections or large deflections. But क्या क्या observations रिकॉर्ड करी गई ये देख लेते हैं. फर्स्ट ऑब्जर्वेशन दैट वाज रिकॉर्डेड वाज दैट मोस्ट ऑफ द अल्फा पार्टिकल्स, दे जस्ट passed straight through the gold foil without any deflection. Second observation was that some of the alpha particles were deflected, but they were deflected by very small angles. The deflection was negligible. And third observation was that some of the particles, they showed very large deflections. They almost appeared to rebound from the foil, right? So from this experiment, what were the conclusions that he drew? First thing that he concluded was that most of the space inside an atom is empty, because that is why the alpha particles were able to pass straight through the gold foil without getting deflected. Most of the alpha particles could pass straight through the gold foil, which means that most of the space which is present inside an atom is completely empty. Now very few particles were deflected from their path, which means that the positive charge acquires a very or occupies a very small space inside an atom. And thirdly, he observed that a very small fraction of alpha particles, they almost had a deflection of 180 degrees, which indicates that this positive charge which is present is concentrated within a very small volume, a very small space within the atom. Now the space in which this positive charge is present is supposed to be the nucleus of the atom, and the nucleus of the atom is, the radius of the nucleus is 10 to the power 5 times less than the radius of the atom. So it's a very small space in which the positive charge is concentrated, the positive part of the atom is concentrated. So Rutherford, because of his observations, he put forward this nuclear model of an atom, which stated, or which said that the positively charged center which is present in the atom is known as the nucleus, and all the mass of an atom is actually residing in the nucleus, because as we have discussed, electrons do not have a significant mass. Their mass is negligible. So he concluded that nearly all of the mass of the atom is present in the nucleus, and the electrons revolve around the nucleus in circular paths. And he also concluded that the nucleus is very small. The size of the nucleus is very small as compared to the size of the atom. Now, again, what the drawback of this model was that, yes, it did. We know that atom is supposed to be a stable entity. Atoms are stable. Now, the revolution, he said that electrons revolve in circular orbit. The revolution of an electron cannot be stable. Why? Because any particle which moves in a circular orbit would undergo some acceleration. And during acceleration, charged particles are supposed to radiate energy. So they would radiate energy, and there would come a point where the electrons, while moving, there would come a point where they would lose all their energy and fall into the nucleus. And if that was the case, then atoms should be highly unstable. But we know that atoms are not unstable. They are quite stable, right? So that was one of the drawbacks of the Rutherford's model. Now comes the Bohr's model of an atom, which made a lot of sense. So to overcome whatever the drawbacks of Rutherford's model was, he put forward a model in which he stated that electrons, yes, they move, but they move only in certain special orbits known as the discrete orbits of electrons. And while revolving in these discrete orbits, the electrons do not radiate energy, so they would not lose any energy, they would not fall into the nucleus. So he stated that while revolving in discrete orbits, the electrons, they do not radiate energy. And these are the orbits K, L, M, and N, also denoted by orbit 1, 2, 3, and 4. And these are the orbits in which the electrons would be revolving. Now we have discussed about electrons, we have discussed about protons. There is another subatomic entity, particle, which does not have any charge. It is neutral, but its mass is equal to the mass of the proton. Its mass is nearly equal to that of the proton, and it is known as neutron. It is also present in the nucleus of the atom along with the protons. Right? It does not have any charge, but the mass is equal to that of the proton. It is represented by N. So mass of an atom is given by the sum total of the mass of the protons and the mass of the neutrons that are present in the nucleus of an atom. That is how we would give out the mass of an atom. Now, how are these electrons distributed in these orbits? So this distribution of electrons was suggested by Bohr and Bury, and he said that the maximum number of electrons present in the shell, they are given by the formula 2n2, where n represents the orbit number, right? The orbit number or the energy level index. So if we are talking about the first orbit, which is the K shell, the number of electrons that it could accommodate would be 2 into 1, which is the orbit number raised to the power 2, which would be 2. Similarly, L shell could accommodate 8, M shell would be able to accommodate 18, so on and so forth. So the maximum number of electrons that can be accommodated in the outermost orbit is 8, right? It is 8. And when the outermost orbit of an atom is completely filled, we say that it has achieved a stable or a noble gas configuration, right? So these are the atomic structures of the first 18 elements. So here we can see the number of electrons are denoted by small dots along the orbit. So if we take the example of sodium, so if we count the number of electrons, 1, 2, 2 in the first shell, then 3, 4, 5, 6, 7, 8, 9, 10. So 8 complete electrons in the next shell. It cannot accommodate more than 8. So 1 electron is present now in the third shell. But it is not stable. For it to be stable, it needs to have a completely filled outermost shell, which it does not have, a concept that we are going to study in valency. Now, valency is the combining capacity of an atom. And how do we understand the valency? Now, we just discussed that to achieve a stable configuration, to achieve a noble gas configuration, it is important for an atom to have an outermost shell which is completely filled. Now, if we take the example of neon, the number of electrons that neon has is 10. So first shell can accommodate 2, and the next shell will be able to accommodate 8. So 5, 6, 7, and 8. And so it has a completely filled outermost shell. 8 electrons completely filled, right? Now, it does not feel the need to combine with any other atom to become stable, because it is stable on its own. It is a noble gas and it is stable on its own. So it has a stable configuration. It has a noble gas configuration. Now, other atoms also want to achieve that. For example, if we take sodium, we just took the example of sodium here. We said that there is 1 electron in its third shell. So if it loses this 1 electron, how can it achieve a stable configuration? It either has to lose this 1 electron so that the second shell is full, it is complete, or it has to gain 7 electrons so that the third shell is complete. One of the two ways needs to be done. But it is easier for it to lose 1 electron than gain 7 electrons. As a result of which it would lose 1 electron to be stable. And because it loses electrons that are negatively charged, it will acquire a positive charge. And because it loses 1 electrons, its valency would be +1. Valency would be 1 and charge on it would be Na positive. So we would denote it as Na positive. Why? Because losing 1 electron is easier than gaining 7 electrons. And if it loses 1 electron, it will have 8 electrons in its outermost shell, which is the second shell, and it would become stable. It would achieve a noble gas configuration. If we take the example of chlorine, it has 2 electrons in the first shell, 8 electrons in the next shell, and 7 electrons in the third shell. Now, to achieve a noble gas configuration, it either needs to gain 1 electron to make 8 electrons in the outermost shell, or it needs to lose 7 electrons. Gaining 1 electron is easier. So it is going to gain 1 electron. Because it gains 1 electron, the charge on it would be negative, and its valency also is going to be 1. If we talk about magnesium, it has 2 electrons in its outermost shell. It can either lose 2 electrons or gain 6 electrons. It is easier for it to lose 2 electrons. So we can represent it as Mg2 positive, and its valency would be 2. That is how we would calculate the valency. And here is actually the valency of different elements which is given. Talking about atomic number is denoted by Z, and it represents the number of protons that are present in an atom. The number of protons determine the atomic number. For example, hydrogen, the atomic number is 1 because only one proton is present in its nucleus. For carbon, the atomic number is 6 because 6 protons are present in the nucleus. If we talk about mass number, mass, as we discussed, is due to protons and neutrons because electrons don't have any mass. So protons and neutrons will contribute to the mass of the atom. Protons and neutrons together, they are known as nucleons. Therefore, the mass number will be given by the number of protons added to the number of neutrons. So for example, the mass of carbon is 12U because carbon has 6 protons and 6 neutrons. Mass of aluminium is 27U because it has 13 protons and 14 neutrons. So to determine the mass number of any element, we need to get a sum total of the protons and neutrons that are present in the nucleus of that atom, and mass number is denoted by A. Now, whenever we have to denote an element, how do we denote it? For example, we have, let's say, a nitrogen. The atomic number of nitrogen is 7, whereas the mass number is 14. So we write down atomic number at the bottom and mass number on the top. That is how we'll denote an atom. Or you can also write it this way. Both the representations are correct. Now talking about isotopes, what are isotopes? Isotopes are atoms of some elements which have the same atomic number but different mass numbers. For example, hydrogen can exist in 3 isotopic forms: protium, deuterium, and tritium. Protium, deuterium, and tritium. Now, atomic number of protium, deuterium, and tritium, all the 3 of them, it is 1. The atomic number is 1, but the mass number of protium is 1, deuterium is 2, and tritium is 3. So even though the mass number is different, the atomic number is same, 1. So these 3 are isotopic forms of each other. More such examples are carbon, chlorine. So isotopes are defined as atoms of the same element that have the same atomic number, but they have different mass number. So protium, deuterium, and tritium, they have the same atomic number, which is 1, but they have different mass numbers. Carbon can also exist in the form of 2 isotopes, carbon 12, where the mass number is 12, and carbon 14, where the mass number is 14, whereas in both the forms, the atomic number is 6. It is the same. Similarly, chlorine can also exist in 2 isotopic forms, where one, the mass number is 35 and the other it is 37, but the atomic number 17 is going to be the same. And lastly, isobars. Now, this is a reverse situation. Isobars are atoms of different elements that have the same mass number, but they have different atomic numbers. For example, if we talk about calcium and argon, the atomic number of calcium is 20, the atomic number of argon is 18, but their mass number is 40. Both of them. Calcium also has a mass number of 40 and argon also has a mass number of 40. Right? So it means that elements or atoms of different elements that have different atomic numbers but same mass numbers, they are known as isobars. Right? So that is all for today's session. Thank you so much, everyone, and I'll see you soon in the next session.